Okay, so we'll make a start. Welcome everybody to this morning's seminar. Today we have Martín López Corredoira, who's going to tell us about two disputes in galactic bulge and bar morphology. Martín has a PhD in physics, but also a PhD in philosophy. That's right. And his interests are wide range in astronomy. They include galactic astronomy, cosmology, and also the philosophy and sociology of science as well. But today, as I said, Martín is going to focus on Milky Way bulge bar disputes. Okay.
Thank you very much. My voice is not very good today, sorry, but I will try to speak clearly. I will talk about the Milky Way, and in particular, in particular, about the center of the Milky Way, the morphology of the center of the Milky Way. This is the image that we think we have about the Milky Way. This is published in the Wikipedia, in the article of Milky Way, this picture, in which we see in the center that there are two structures denominated as bar, galactic bar, and non-bar, just to distinguish both structures. This will be one of the topics of my disputes today. I will talk about two disputes, two debates that are still open, and one of them is the nature of this structure. Whether we are talking indeed about a double component, or it is the same component and one is an extension of each other. Let's start looking at other galaxies. Here I have, for instance, another example, and see whether we see something similar to what we observe, what we think we observe in the Milky Way. This is NGC 3992. And here we have the composition, the composition. In the left panels we have the images, and in the right panels we have a model. We can see here that there is a long bar, quite clear, and once we remove the disk and the long bar, we have another structure in the center, which has a different angle indeed. Not aligned with this one. So the answer is positive. Effectively, there are other galaxies in which we can see these double structures. Also, from the theoretical point of view, there have been some analysis contemplating the possibility of a double bar. Bear in mind that I'm not talking about a minor nested bar embedded in the major bar. No, here we are talking about two major structures. Already in the 80s, there were some analytical studies talking about the evolution of two triaxial structures and how they will evolve with time, whether they will collapse and form one structure alone or not. And the result was not surprising. Indeed, if we have two different structures with different angles, we will get a harmonic oscillation with the angle between the two, and this will last for a long time. If we allow the size of the bar to be changed, also we have more complex motions, but the bars can last, the two bars can last for a long time. On the other hand, from a different point of view, there are the analysis of the formation of these structures. And the last papers about this, for instance by Martín who was working here in the IC, and other people, Atanasola mainly, they talk, rather than a bulge, they talk about a pseudo-bulge, which is formed from the instabilities of the disk. In such a case, they claim that there is only one structure. There are not two structures in the formation. There is only one structure, and possibly what we call the long bar is an extension of the inner bulge. This is the topic that we want to analyze here more in detail, because it's still a topic that is being discussed nowadays and it has not a clear solution. There are some observations that point out the existence of both structures in the Milky Way. About the short bar or the triaxial bulge, there are already evidences as early as in the 60s, but mainly in the 90s, about the triaxiality of the bulge. It's non-axisymmetric, mainly from the radio observations. Also from the star counts, the COBE in near infrared, and finally with star counts of 2 mass and others. On the other hand, we have evidence of the lombard strictly in the plane, which is much larger than the bulge, and with a different angle from different observations also from Peters, Weinberg, Hammersley, here also, and we'll talk about it later, etc. Let's see in detail some of these observations. For instance, these are the maps of Kobe produced in the 90s. These are the flux maps of the center of the galaxy. Here we see the raw data. Here the data corrected of extinction, near infrared corrected of extinction. And here the flux once we subtract the disk component. And we can see that the residuals are non-symmetric. There is further flux in the positive longitude than in the negative. This can be only explained as triaxiality of the bulge. This was the picture of the bulge that we have in the 90s. The same thing can be observed using the star counts, for instance, of 2 mass. If we take the total star counts of the center, in the K band, for instance, we correct of extinction, we subtract a model of the disk, and we obtain something like this. Clearly, this bulge has further counts, more counts here in the positive side than in the negative side due to the triaxiality. Even with some techniques, some Bayesian techniques, we can obtain three-dimensional plots of the density of the bulge, as we see here. These are some slices of different heights at different distance from the plane, and we can see which is the structure of the bulge, as we will see face on. It is not only triaxial, as we say, but only we see some boxiness. So these are not perfect ellipsoids, but there is some, the corners are more closed, so we think it's more better represented by a boxy bulge, in agreement with other studies also. This was the analysis made in 2005. The question is that after we subtract the disk and the bulge, still in the plane there are some extra residuals that we cannot explain either with this model of the bulge or the disk. And this is important only for very low latitudes, galactic latitudes. As we can see, with a model of the bulge here and the disk, more or less we represent the counts. But if we go to very low latitudes, we have some extra counts that need an extra component. This extra component is precisely our lombard. There are some other evidences of the existence of this lombard. For instance, using the red clumps stars, which are a standard candle, usual standard candle, in the year 2000, Hammersley and collaborators, our group here in IAC, could measure the distance of this structure up to longitude of 27 degrees, more or less. And we can see how this peak of the counts of the red clumps is moved with the longitude and can be represented in a plane of the x and y, the galactocentric coordinates. If we measure the angle of this lombard, we get an angle around 43 degrees, which is different from the angle that we have obtained previously for the bulge, which was around 25 degrees. This is the angle between the major axis of the lombard and the line joining the Sun and the galactic center. Also, we have measured the half length of the bar is around 4 kiloparsec, while the bulge is only 2 or 2.5 kiloparsec, so it's a much longer structure. This is the picture, the idea that we have about the center of the galaxy. This picture was produced already in 2003 or 2004. And here we have a representation of the bulge in the center, which is much thicker, so it can be observed in off-plane regions, and the lombard, which is only observed in in-plane regions. Fortunately, this observations, and this hypothesis was later confirmed independently by another group, an important group, the Spitzer glimpse data, confirmed this picture using more or less the same technique. Sorry. Sorry. Yes. The Spitzer glimpse data confirmed this picture, the existence of the lumbar, and they obtained also more or less the same angle, 45 degrees, and the same extension, 4 kiloparsec arm, but using this data, Spitzer eclipse, which is a different wavelength. It's infrared, but slightly different wavelength. Precisely due to this success of this confirmation, the standard picture since 2005, in 2005, will be something like this. This is the artistic representation of the galaxy inspired by the Spitzer glimpse data. And here we see the representation of the lumbar and the and the bulge. The question will not finish here, and there will be further discussions. In 2015, Martínez, Valpuesta, and Gerhard proposes a model in which both things, the bulge and the lumbar, are the same structure, but one is an extension of other. And in order to justify the different angle of the lumbar, they say that the bulge in the end twists a little, changes a little bit the angle. We have our group here in ISC has replied this proposal, and we think it's a reasonable proposal. Why not? In principle, talking about double bar or single bar with these extensions might be a semantic question. It's just a way to name the things. However, we must bear in mind that apart from the morphology, there are other characteristics. The lumbar and the bulge have different stellar populations. We know indeed that there are different ages of the stellar population, different metallicity distributions. There are also some star formation regions associated to the tip of the bar, and also there were also some facts that were not explained by this model, that this lumbar was too thick indeed in the vertical extension and also in this extension compared with our data. Here we have some reference about the study of the metallicity in the lumbar stars. This old one by González Fernández et al. Finds precisely that the metallicity in the lumbar is more similar to the metallicity in the disk stars than in the bulge stars. So if the metallicity is different, we should think that the formation process cannot be only one. There should be several stages to form this structure. A more recent analysis is given by Beck, Gerhard, and collaborators, in which they find, surprisingly, that it's not even that the metallicity of the lumbar is similar to the disk, but it's even over the disk. It's 0.3. In my opinion, these numbers are difficult to believe. A metallicity of 0.3 is quite difficult, but this is their analysis. In any case, what it is clear from any of this analysis is that the metallicity of the lumbar stars is very different from the bulge, and there is a very strong vertical gradient in the separation between the lumbar and the bulge. This is a more recent proposal by the group of Gerhard, precisely, Beck, Gerhard, and collaborators, in which now they have corrected their previous model, and the bulge and the bar in this time is not twisted, but is totally aligned. And in order to justify that the difference with the observation, they claim that the previous observation of the measurement of the angle of the bar were affected by systematic errors, mainly from the extinction correction, and they have remeasured again the angle and obtained an angle of between 28 and 33 degrees for the angle of the lumbar. So this, according to them, this make it more or less compatible with the angle of around 25 degrees measured for the bulge. The angle for the bulge is quite well established by many groups, and it's around always between 20 and 30 at most. No? However, this year, with the Gaia data, some group, Anders et al., made a measurement again about the angle of this structure, and they found, correctly, they found a structure which is 4 kiloparsec, the semi-axis of the lumbar is 4 kiloparsec, and they find an angle of 40 degrees using the parallaxes and with some Bayesian methods to correct the parallaxes and to do the statistics with that. So again, we have the doubt whether the angle is 30, 40 degrees. This is the state of the debate, of the discussion nowadays. Nowadays, the people defend some people defend it's only one structure. We are talking about the same thing. The lumbar is an extension of the lumbar. Other people, like our group, have decided to support the idea that we have a double bar, whatever it is the origin of this double bar. And it is not only a semantic question. It's only we have to bear in mind that there are also different populations. So this has to be in mind. Any model of the galaxy proposing the formation of the pseudo-bulge should be able to explain these different ages and different metallicities of this new structure, which is the lumbar. The angle of the lumbar depends on the group. Some people, the defenders of the single bar, claim that it's 30. Other people, most of the measurements, glimpse, Gaia, our measurement, claim that it's closer to 40 or 45 degrees. This is still not clear. Effectively, it's not so easy to measure the angle because there are some systematic errors, for instance, extinction correction, etc. It's not so evident, but there are most of the studies point more closer to 40 degrees. However, the angle of the bulge is between 20 and 30 degrees. My conclusion is that this is a topic that is still open. There are no conclusions nowadays, and we need further research, especially in the area of the lumbar, which is particularly here, in the areas between 15 and 30 degrees in longitude, either positive or negative, and also in galactic latitude less than 2 degrees. This area was not well studied enough. So there are plenty of studies in the bulge, but in this area of the lumbar was not enough studied. It's difficult also because the extinction in the plane is much higher than infrared, and the spectroscopy there is complicated. But I think it's worth to make an effort in this direction. So this was the first debate that I wanted to mention, and now I move to a second debate, which is also about the morphology of the bulge, but not the morphology of the bulge as we see it face on, but as we see it edge on. I explain it now. In the literature, the recent literature, there are different models predicting which should be the shape of the bulge. The older studies, all the studies from the 80s, 90s, predict that the bulge seen edge on should be something like that, with something peanut or boxy shape as we see here. However, more recent analysis of the people making dynamics simulations of the galaxy claim that there should be a strong X shape when we see the bulge edge on projected. Not only a boxy, we see the difference. The difference is that here, of course, we have a gap, but also here we have a gap of stars, which is not observed here. This is the difference. No, this is the X shape. Inspired by these theoreticians, by this analysis of the theory, there were people trying to find evidences of this X shape. And here in the Milky Way, in particular, here we have perhaps the most important analysis of the photometry of our galaxy with WISE data in infrared that trying to find the X shape. And they claim they have found it. These are the raw data. They have to make corrections of extinction. They have to subtract a model of the disk. They subtract also a model of the bulge, average bulge, and after that they obtain something like this, which is clearly an X shape. This result was taken very seriously, apparently, because it was even in the poster of the presentation of a Galactic Bulge conference last year in the ISO in Chile. So people is taking seriously this result. One may wonder, however, how is it possible that in the 90s, for instance, with the COVID data, nobody has seen any X shape, and now with similar data, of course they are deeper and have some different characteristics. This is flux, here we have separation of stars, but deeply is not so different. The concept is not so different. Why we have not observed an X shape here, and however now, 22 years later, we see an X shape? And the answer has to be with the many possible systematic effects in the analysis of this data. These are the raw data. In order to obtain this, we have, as I said, we have to do corrections of extinction. We have to subtract the disk, and even in this case, they subtract a bulge using an ellipsoidal instead of a boxy. According to some authors, like this reference that I put here, the fact that they use ellipsoidal bulge instead of boxy bulge produce some artifacts, some residuals that can be confused with an X shape. Therefore, although we cannot be sure who is right or who is wrong, maybe Lee is right, or maybe Ness and Lang are right, or the COVID analysis are right, we cannot be sure. The thing that we can cast upon doubt this result. This is not enough. This Ness and Lang paper is not enough to support the idea of X-shape, because it depends on the model. It depends on the model of the disk and other models. We need some further proofs. This was the X-shape observed in the tangential line, tangential to the line of sight. If we want to observe the X-shape along the line of sight crossing the bulge, we will, let me take the microphone, difficult, but no, if we have an X-shape like this, a line of sight not crossing between the X-shape, has a double peak. The thing that I wanted to explain. So with this idea in mind, people has used again the red clumps taken from the color magnitude diagrams, and tries to find double peaks along the line of sight in off-plane regions of the bulge. And certainly they found it. And not only one group, many groups have found the same result. So this was corroborated in many ways, always using the red clamp as standard candles. We see here how selecting the red clamps, we put the star counts, and along the line of sight we see a double peak that they have interpreted as the evidence of the X shape along the line of sight. If we use all the lines of sight and of the bulge, and we combine all the information, we can produce some maps like here, produced by Beck and Gerhard, for instance. No? We see these are different slices, different cuts of the morphology of the disk at different heights, or different distance from the plane. This is 1 kiloparsec, this is 260 parsec. We can see that near the plane we see only one peak, and if we move away from the plane we see a double peak. As it is expected by an X shape, precisely because in an X shape you get a separation of the wings if you move away from the plane. All these analyses are based in the assumption, in one important assumption, that the standard candle, the red clamp, is a perfect standard candle. So all the stars that we are observing has the same absolute magnitude. Of course, the red clamp is a very useful tool to investigate the structure of the galaxy, and it was known since many years ago that using, particularly in infrared, because in infrared is almost independent of the metallicity of the population and on the age of populations too. We can see that, for instance, if we plot the absolute magnitude and the color of the color magnitude diagram, we can identify clearly the red clamp, and these are quite concentrated in a narrow region. Nonetheless, and this is the point here, there was some warning by some authors that there may be a secondary red clamp. In some cases, for instance, in cases when there is helium enhancement, as it is observed in some globular clusters, or in some cases in which there are different ages of the population, there may appear a secondary red clamp. And this, for instance, in this paper by Girardi, has demonstrated the existence of this secondary red clump using the high Parkov data that were available at that time in the solar neighborhood. So it's not only a theoretical speculation, but it is there. And this idea of the secondary red clump by Lee et al. Was also tested with some global clusters. So in some cases, not always, but in some cases, we see a duplication of the red clump. So this can be a problem for this proof of the red clump, because, of course, it is clear that we have two peaks along the line of sight of star counts, and this can be interpreted as two peaks in density, assuming a constant luminosity function. But it can be interpreted as a double peak in the luminosity function too. How can we distinguish this degeneracy of the solutions? The only idea that I have to solve this problem is just trying to find another independent standard candle and trying to find the same X shape. Do not use the red clump, use another standard candle and try to find this X shape. Indeed, the predictions are quite different for the different models. This is what one will expect from a boxy Bulge model. This is the slice at 1 kiloparsec from the plane, and this is the X-shaped model. So the predictions are so different, so we are able to distinguish. Here I show you some of the analysis that I have been doing about trying to find this double peak with different populations. One possible standard candle, although it is not as perfect as the red clump because the uncertainties in distance is much higher, is selecting the very bright stars of the main sequence, the F-type stars of the main sequence, which have a magnitude around 2.4 absolute magnitude, but is still possible to be observed in the vista survey. These are representative of a relatively young population, 5 gigayears. So this is not the most of the population. Most of the population in the Bulge is older. But we know nowadays that there are some stars younger than 5 gigayears also in the Bulge, even if it is not the majority. And we can select it using the color magnitude diagrams, correctness of extinction, and so on. If we select these stars and we plot the density of these stars as a function of the distance, this is the result. We see clearly only one peak, not a double peak, only one peak. And must be correct because the peak is centered in 8 kiloparsec, as it is expected. This is the distance of the Bulge, and we don't see a double structure. These are the predictions of the model. If we have a X-shaped Bulge, we will expect something like this, a double peak in this latitude. We are talking about latitudes of 7 degrees, 8 degrees. These are the same lines of sight that have been used for the red clump. Of course, we have to take into account one factor, that here the accuracy, the determination of the distance of these stars is not as good as in the red clump. There is a dispersion of absolute magnitude, particularly is a RMS of 0.2 magnitude, which makes an error of maybe 20% in distance for each individual stars. And this produces a convolution on the models. Even if we take into account this convolution as we do here, we see that the peak is less significant, the double peak is less significant, although should be observed. And what is clear is that this structure should be much thicker, not as concentrated as here. This result fit perfectly the prediction of a boxy Bulge with only one peak, and do not fit at all with the X shape. So we have one result, that at least we know that for the young population, less than 5 gigayears, we don't see the X shape, we see a boxy Bulge. Let's see another standard candle that we have used, which is the variable star, the Myra variable stars, or rich, which are, in this case, the determination of the distance is much accurate, the error of distance around 4%, using the period luminosity relationship, at least in infrared, which is the data that we have used. And again, making the same analysis, plotting the density of these stars along the line of sight, we see only one peak, clearly one peak. Well, the problem here with these stars is that we have very little. We have only a few hundreds or thousand stars, so the error bars are considerably high. But even so, making the statistical analysis, the predictions of a double peak done by the X-shaped model are excluded at least at 3.3 sigma. And on the other hand, the boxy bulge, which predicts only one peak in this line of sight, fits perfectly this data. And we must bear in mind that these Mira stars are the same age on average than the red clamp, are on average have 9-10 gigayears. So we are tracing more or less the same population that should be traced by the red clamps. A third population was also used, in this case by a different group. For instance, Petrukovic with the OGL data, they have used the RR Lyrae, which are representative of very old population, older than 12 gigayears, and they have observed again only one peak along the line of sight instead of a double peak. Therefore, the scenario is we have a strange scenario here. We have the result that with the RR Lyrae, which are very old stars, we don't find any X shape. With the Mira variables, we don't find any X shape either, and with the young population of F-type main sequence, we don't find any X shape. We only find X shape with the red clamp, and only in the red clamp with metal-rich stars. If we go to metal-poor stars, as was demonstrated by Ness et al., we don't find either the X shape. This is something to suspect about the validity of the using the red clamp, metal-rich red clamp. Maybe there is something strange in this. These standard candles are not so standard. Can we do something else to check the validity of the hypothesis that the red clamps have the same absolute luminosity, absolute magnitude? Yes, we can do it, and we have carried out very recently using the Gaia data. Again, we have taken the lines of sight that cross the X shape quantitatively, the same lines of sight that have been used for the red clamps, and we have obtained, of course, the star counts a function of the apparent magnitude. Clearly, we see the double peak, of course, the bright red clamp and the faint red clamp. If we use the cross correlation of the Vista survey with the Gaia data, apart from using the color magnitude diagram, we can obtain also the parallaxes. And with the parallaxes, we can estimate, on average, of course, individually, we know the error bars are huge, but statistically, we can obtain the average, or the median, in this case, the median absolute magnitude associated to these stars. This can be done, as I said, because we have thousands or tens of thousands of stars. Otherwise, we could not do it. And here it is the result. Surprisingly, here the absolute magnitude of these stars is not a constant. Depends on the apparent magnitude, and we see clearly that the faint red clamp and the bright red clamp, on average, I mean, have not the same absolute magnitude, but there is a difference around 0.4 magnitudes. This difference of 0.4 magnitudes is, by the way, in agreement with the predictions by Lee et al., the model of Lee et al., that claim that indeed one of these red clamps is produced by helium-enhanced second generation red clamp. They also predict a difference of 0.4 or 0.5 magnitudes. Nonetheless, we must bear in mind that there are other, apart from helium, there are other possibilities. Strong changes in metallicity can affect, and in age, as we have seen with the Girardi paper, if there is a strong difference in age of this population, we will see also the difference in the absolute magnitude. The question is that once we take into account this 0.4 magnitude of difference between the standard candles, the hypothesis of the X shape is not kept because this is maintained on the distance produced by the double peak of around exactly 0.5, 0.6 magnitude. So most of this distance that we have seen about the double peak is not due to the distance in the density distribution, but something associated to the luminosity function of the standard candles. Therefore, my impression is that we cannot trust either in the red clamp analysis or the X-ray. Some people this year also, there are some recent analyses that claim it, but we have also used Gaia to measure the proper motions of these stars, the faint red clamp and the bright red clamp, and we have seen that they have different proper motions. The question is, so what? Yes, they have different proper motions, because if you move half a kiloparsec or 1 kiloparsec beyond, forward or backward, you will change the sample of the stars, and they have different velocities, of course. But this does not demonstrate anything. Indeed, there are some papers, for instance, by Lee et al. Here is an error, 2017. There are some papers demonstrating that with the proper motions, we cannot distinguish both models. The boxy bulge and the X-shaped bulge cannot be distinguished with the proper motions only. So this analysis, this recent analysis, does not have any element, just to clarify the question. My conclusion is that, of course, the problem is still open, not closed, but if somebody wants to defend the existence of an X-shaped bulge in our Milky Way, has to use a standard candle different from the red clamp and demonstrate that the X-shape is there. The red clamp, as we see, may have some problems, because it's not as can be contaminated by the secondary red clamp. So that is all. I think I finished sooner than expected. I have 2 slides. Just my conclusions are the conclusions that I have pointed. My impression, I always defend that we as observational astronomers are being too much influenced by the theoreticians. When some theoretician proposes some model, immediately the observers try to confirm this model. This is not the way how empirical observational science like astrophysics should work. Should be the inductive method. First we observe, and then the theoreticians should build the model, not the opposite. We are not here to confirm the predictions of the theoreticians. And this, we are observing, this is especially true in cosmology. We always have the theoreticians pushing the observers to find what they want to find. No? But here in the galaxy, we have also this pressure. It's enough that some important teams of dynamicists claim that they predict the existence of X-shape, and the observers go just to trying to push the data to confirm that. No, it should be the opposite way. The data are what they are, and the theoreticians should adapt to the data. This is my impression. And that's all. Since we have finished sooner than expected, I think there is time for questions.
Thank you, Martin, for that interesting talk. Okay, so we have time for questions, and I can see various hands. So, okay, Karma first.
Okay, you made a good review of what is the discussions in the field. Okay, I think using these F stars in the main sequence to trace the bulge is a very bad idea, because the bulge, even though there is a strong discussion on whether there is a population of intermediate age in the bulge, but it would be a minority population in any case. So I don't think you are tracing the bulge when you do that. I think you are tracing the disk, and so this result doesn't really convince me at all. Then about the several clumps in the bulge, yes, they can be. In any case, if it is a population, if you refer to the clumps that are due to stellar evolution, then there always will be a majority clump, in particular the secondary clump that you mentioned there, quoting Girardi, could be a clump made by around 1 year-old stars, which are not seen in the bulge anyway. Okay, then the helium hypothesis, I wonder why they are not measuring spectroscopically whether there is these different helium stars there. But in any case, if you had a double clump, you would have it both in the closer region and in the farther region. which would produce, in any case, an elongated structure. So I don't see this also. How can you solve this problem? Or I mean, how can you refute that it's a next shape because of this, because of that double clamp that exists due to other reasons, but it could exist both in the inner of the closer side and in the farther side.
For the first question, it is true that there is still a discussion whether there are enough F-type stars, enough young stars in the bulge. Some people have put some constraint that there is only 3% of stars younger than 5 gigayears. Other people, like Bensby, for instance, claim that there is as much as 30% of stars younger than 5 gigayears. So it's still a topic of discussion. They base their analysis in spectroscopy and all that. So it's an open question. What it is clear from this thing is that these stars that I'm selecting here, assuming the correction of extinction is correct, these are low extinction regions in any case, have a distance of what we see here is are centers in 8 kiloparsecs from the sun, so they are not nearby stars. No, the only one. No, because there is no disk in the bulge. There is a hole. There is a hole in the disk. In these areas, the disk contributes very little. So the disk grows exponentially, and then for the inner 4 kiloparsecs, there is a hole that decreases suddenly. There are many studies about that. But in any case, your doubt is reasonable. I accept it. The second question, I'm not sure whether I understand correctly. Certainly, I agree with you that it's not very likely that we have populations younger than 1 gigayear, like the Arctic, for example. It's one hypothesis, but it's not very realistic. The hypothesis of the helium, however, this is the hypothesis of the Korean group of the Lee et al. However, has been tested in some globular clusters, even in the bulge, for instance, Tarzan 5 or other, and they have found it. It's not only a theoretical speculation with the isochrons and so whatever, but they have also observed this double red clamp. The thing is that, of course, assuming that the whole bulge behaves like the globular cluster is a big hypothesis, and we have no proof about that. You tell me why we have no evidences for the helium. Well, the helium in spectroscopy is very difficult to measure. Indeed, now we are thinking of ways to measure doing some spectroscopy of the stars. Apparently, the sodium should be correlated with the helium. So possibly we should analyze other elements that are correlated with helium. I agree totally that there are no evidence enough that we have a general helium enrichment in the whole bulge. We need further tests, but also the opposite is also true. We have not evidence of the opposite. When I mean helium enrichment, I mean the value of Y.4 instead of 0.25. So it's 0.35, 0.4. This has been observed in few cases, as I say, in globular clusters, but we have no evidence enough that this is the case. Precisely because of that, we need further research. Maybe you are, I have not understood very well your question, but maybe you are surprised why the shape, the distance between the peaks changes with the latitude. No, it's not your question, no. Then I have not, yes, because I have not understood possibly correctly. Thank you. Well,
the idea of the helium is a very interesting one. Um, there are some evidences that have been dropped in several, especially in globes, globe clusters, to explain things like, for example, the ultraviolet turn and things like that, like anomalous or very high helium, let's say. And regarding, but my main question is that these residuals that you get, for example, for the X, no, the X-shaped residuals, no, is any spectroscopic counterpart for those stars? I mean, that you, for example, you can use the Gaia, or you can use apogee or whatever, that to test. I mean, what can be learned from the spectroscopy, radial velocities, for example, or any properties like temperature, mechanicity, abundance, which would be really key at this point. If there is a difference related to the X shape, this is probably an answer to the question.
I agree. I think it's a good question, and we are working on that. Precisely, we have now Paco and Carlos Allende, and we are trying to use apogee data just to get further information about this, particularly about the faint and rest clump of these peaks, no, of these two peaks. On this X shape, as far as I know, nobody did the analysis, just trying to see whether these winds of the X have a different property than the rest of the bulge. I have not seen, but it's also a good idea, possibly, just to see if it is real, this thing, and it's not an artifact. We think it's an artifact indeed. But if it were real, maybe we should see some different properties in the orbits of these stars that produce the X shape. Yes, it's not easy in any case to make a you need a very wide sky area just to survey, and doing spectroscopy is very special, but we have now apogee. We are trying to use the apogee just to get the more. Yes, the thing is that indeed we have 10,000 stars, but for instance rest clumps, so there are 200 stars or so, no, in rest clumps. We are trying to get, for instance, the spectroscopy of these stars, and in the end we have only But of course, I agree. We need further analysis in this direction now, because with photometry we have done all that can be done. Now we need something better, spectroscopy.
John.
I have a question and a comment. The two are different. The question is, you mentioned that one of the key pieces of evidence for the long bar is the star-forming region at the end of the bar, found by spectra of giants and identification of distances. So my question is, this has happened. These data are quite old. Are there equivalent data for the far end, the other end of the long bar? Because with the progress of infrared measurements and fibers, it should be possible to repeat the process, and that would strengthen very much the story about the long bar. So that's the first question. I'll make the comment before I. The comment is this: about your claim about inductive and deductive reasoning. I have a very good counter-example. In the 1980s, observers presented rather sharp truncations in galaxy disks, and the theorists went away and produced models for these truncations, very good models, beautiful theoretical models. It turned out that the measurements were wrong. So you can work it out both ways. It can go both ways. I agree with your comment, really, but it can go the other way as well. It can be mistaken. The theorists are very clever. They can produce anything. So it's not a safeguard just to show them data. Anyway, please answer the question.
About the last comment, certainly, yes, of course, the observers should do the work carefully. And the thing that I want to point out is that we should be neutral, not to have any prejudice in mind when we do our analysis, but we have to do our work correctly. If we see truncations where there are, and we have not taken into account the flare or whatever, you know, what is the answer, no? This is a wrong analysis. But my point is that we are very much influenced nowadays by the fashion theories that we have now. We should be more open-minded, no? When we analyze the data. About the star formation regions, I mentioned it because, for instance, in this model that was presented by Martínez, Valpuesta, and Gerhard, they have not predicted any star formation regions in the tips. And however, we know there is at least one in L27, as you know, and according to Peter, who is here, there is another one in L-22, in the negative side. Of course, in the L27 we have confirmed it spectroscopically, but in the L-22 not spectroscopically, but we have seen a huge number of supergiants, which is more or less enough to claim. No, not yet. Yes, please. Yes.
Really the problem is at the moment we don't have the big wide field infrared spectrographs. So when Moon comes online in a couple of years, one of the projects that they're going to be doing is the inner galaxy, and they'll be able to do that whole region. And that's got 1,000 fibers, does J and H in one go. Moons. And so really the problem is that there aren't the wide field spectrographs. I mean, the only MOS at the moment is KMOS, and that's mainly doing external galaxy stuff. That's really the problem.
I don't know if you want to comment on that, Martin. Or okay. Okay. Time for one more question. Quick question, if anyone has any comment. I have a comment or a question on your last two slides, actually, the deductive and inductive part. So it's sort of you're suggesting that there's been a cognitive bias in the sense that people have been finding this X shape when it really didn't exist. You're suggesting that the key reason has been this? There's been a bias in thinking this, driven by the theorists' results. Is that what you're suggesting?
I'm not a psychologist. I cannot know what is in the minds of the people. But what I know is that, for instance, in the 90s or on the beginning of this century, when there were no X-shaped models produced by the theory, nobody has seen an X-shape. You took the COVID data and you made your analysis and you don't see anything. And suddenly some theories come to the literature, and they are produced by powerful groups, and they are the new fashion ideas in the beginning of 21st century, and suddenly people start to see X-shape. So this is possibly a coincidence, but I think there is an influence. We are not being totally objective. Yes, there is a comment.
There has been the possibility to measure in a star by star. I mean, the measurement by Jokali and McWilliam, for example, I think is a very, I mean, there is a very simple and reasonable assumption that the red clump is very approximately a standard candle, right? And that one is just that before you didn't have these resolved stellar population. You couldn't measure that in resolved stars, and this makes a difference. The COVID data is integrated light. This is measuring distances star by star, almost. And I think this is much more trustworthy.
The thing is that the methods of the red clump was already known in the 90s, and this was used in the 90s. Yes, it was stars in the Bulge. Yes. Invisible, at least, there were surveys, Ogle in the beginning of the 90s or the later. There were already data available to make the analysis. And the first analysis pointing that the red clumps have something related with X shapes came in 2010, much later than by these people. There was another paper, I don't remember the reference, but produced in 2007 by another group that already realizes that the rest clump has some double peak, but they have not taken, it's an important question, and they have avoided to discuss about that. So the thing is that already in the 90s, we have the tools to see the X shape, but nobody in the 90s have seen it. And already in the 90s, we have the photometric maps in infrared. For instance, the COBE or also the 2-mass survey was available in the beginning of the, and nobody has seen any X shape in the beginning of the 21st century. So people has waited for the theories to be available, and then once you have a theory predicting the X shape, people start to see X shape. What is a strange coincidence, no? And this is not the first time that I observed something like this in galactic astronomy. For instance, many years ago, I was working in the topic of monoceros and the Canis Major, that is, suddenly cosmologists started to say, no, we have to see many dwarf galaxies around, many tidal streams, because the theory predicts that we should have many tidal streams. And people started to discover new streams. Some of them were correct. Sagittarius, for instance, is a dwarf galaxy, but others, I think, were pushed by this pressure of the community, the cosmologists, that tried to find new evidences of this. So this is what I mean, that we, as observers, I totally agree, John Beckman, that also the opposite cases also happens. No, the observers can make a blunder, can produce a wrong result, and induce the theoreticians to do a wrong theory. So we have to be in interaction with each other. But we should be like lawyers. One lawyer, when defends somebody, does not believe anything, whether he's guilty or innocent. Just present the proofs, and that's all. This is what we should have in mind, presenting proofs about evidences, about how are the data. And the interpretation should come later. But if you have the interpretation before doing the observations, you have prejudices, my impression.
Okay, I think we should stop there. We can continue. We now have scientific coffee in the cafeteria. Okay, thank the speaker again.